All right, hi everybody, welcome back to 10600. So I think the first thing that I wanted to do today was to go over the process of finding the coefficients of a vector and a basis, like in the homework assignment that you guys just completed on Friday. Get that started. So we posted is that big enough? That should be big enough. So we posted a simple example in on Piazza. So let's just go through this example. Let's just go through this example. All right. So this is a simpler example. We're in just a two-dimensional vector space, and we know that we have basis vectors b1 and b2, right? So what do we need to know about the basis vectors? We need to know their matrix of dot products with each other. So we have, for example, that well, the inner product of b1 and b2 is 2, and the inner product of b1, sorry, is a half, right? That's this element right here, and the inner product of b1 with itself is 2, right? And there's only 3 distinct ones, so the inner product of b2 with itself is equal to 1, right? So those are the 3 distinct elements of this matrix B. And what we would like to do is, sorry, just a sec. Let me make sure that I'm connected up to get chat messages from the TAs, in case people have questions. All right, so now going back here, so this here, these dot products between pairs of basis vectors correspond to this matrix B, right? And in your exercise, you were given, I think it was 35 different basis vectors, and you were given an equation for calculating their inner products. But here, there's only 2 of them, and we're just going to list out their inner products. And now, suppose that we have a vector x, and we know that b1 inner product with x is equal to 1, and b2 inner product with x is equal to -1, right? So then what we can do is we can write out a linear equation to solve, right? So that linear equation is b x tilde is equal to q, where here x tilde are the coordinates we want, right? So what we're trying to do is, given a vector x, find its coordinates x tilde. B comes from this information here. In particular, it's the matrix 2, a half, 1, where the ij element is the dot product of bi and bj. Right? So that's B here. And Q comes from this information here, right? And in particular, Q is the vector 1, -1. Its jth element is the dot product of x with bj. All right? And we can just give this equation, right? So if we write out this equation here, that is this equation right here in the Piazza. And if we give it to MATLAB, we can just solve it to find this value of x tilde, right? And so that means in particular that x is equal to 0.857 B1 plus, minus 1.429 B2. And you might want to check your work, and if you want to check your work, you can, for example, compute the dot product between x and b1, right? So we know that's supposed to get 1, and so the dot product between x and b1 is 0.857 b1 minus 1.429 b2 dot b1. Sorry, I should be saying inner instead of dot. Right, so this is the expression for x, and we want its inner product with b1, and we know that inner product is linear in its first argument, so we can split out 0.857 b1 inner b1 minus 1.429 b2 inner b1, right? And so I just pulled the subtraction and the scalar multiplication outside the inner product. And if we check this, this is indeed 1 to the precision that we're working in. All right? So everybody please feel free to ask questions about this example. Hopefully this example is fairly clear because it's in 2 dimensions and we can work out everything with not much more than a calculator if we want to. So now let's go back and I'm going to take a look. Earlier this morning I posted the solution, the code for the solution to the Friday exercises on Piazza. Right, so here's the code. Let's do this and scroll so that we can see all of it. Right, so this part here, this is just the problem data that's copy-pasted from the assignment. And then here is the solution. And so I'd like to go through this line by line. And again, the goal for this is to make sure that everybody can ask questions if they don't understand what any one of these operations is doing. So in order to understand this, you need to know what BSX-fun does in MATLAB. BSX-fun is MATLAB's implementation of broadcasting. So here what it's doing is it's taking a function and it's applying it to 2 matrices, and it broadcasts the matrices to make sure they have the same dimensions. So here centers is input as a row vector into MATLAB, so centers transpose is a column vector. So a column vector minus a row vector, and that's going to give us a matrix where every element is the difference between element I of centers and element j of centers, right? And then we component-wise square that, multiply by minus 0.5, and exponentiate, right? And so what we're doing here, right, this line computes the inner product of every basis function with every other basis function, right? So our basis functions, if we grab a new page, our basis functions are B1 up through B35, and each one of those is given by the formula that was on the assignments page. So for example, B4 of y is the function exp of minus y minus 7 squared over 2. Where did I get 7? This 7 right here. That 7 is the same as this 7 here. It's the 4th element of this centers vector, right? And so, you know, at the end, B35 of y is exp of minus y minus 50 squared over 2, right? And that's the last element of centers. Okay, and so what I've done here, and we have the expression that B sub, for example, if we wanted the inner product between these two, we would say that the inner product between B4 and B35 is B4 evaluated at the center of B35. So it's B4 of 50, which is exp of minus y is 50 here, 50 minus 7 squared over 2, right? And so this is going to be a very small number, right? 50 minus 7 is 43. 43 squared is, you know, not quite 2,000. So exp of minus not quite 1,000 is a very, very small number, right? So that's approximately equal to 0. Meaning that B4 and B35 are almost orthogonal. Okay? So what I'm doing then, I'm taking here this that line computes the matrix B, whose ij element is the dot product of bi with bj, right? And then Q, right? That's the dot product. If we scroll back up to our previous example here, right? Q is just supposed to be the dot product of our target vector with every one of our basis functions. That is exactly this vector right here, the dot prods vector. And so what we want to do is solve the linear equation with matrix B and right-hand side dot prods. So a little bit about MATLAB notation here. The parenthesis colon turns it into a column vector, and the backslash is MATLAB's equation solver. It will actually find the LU factorization of B for us, and then backsolve to get twice to get W. Right? So in other languages, it might take a lot more ink to get the same thing done. In MATLAB, solving a linear equation is one character, which is kind of convenient. And so now this W here, that W is the same as x tilde from the assignment. All right. And then the last thing that we have to do is plot it, right? And so what we want to do, so W equals x tilde, right? So what this means is that our function is equal to sum over I of W of I times B sub I, right? And so if we want f of x, that's going to be sum over I of W of I times Bi of x, right? Because linear combination of functions just means linear combination at every argument. And so if we want to evaluate this, we have to evaluate Bi of x at every x that we want to look at. And so what I've done is I've picked a grid here. This is a bunch of points running from 1 through 50 at step 0.3. You could choose a different step. There's nothing special about 0.3. It just needs to be small enough that the line looks smooth when we plot it. And now what I'm doing here is I'm evaluating, this line is exactly the same as this line, except I replaced centers here with grid. And so what I'm doing is I'm evaluating every basis function, right? Every basis function, one for each center that I have, at every grid point that I'm interested in plotting. And then here we just plot it. And the important part here is this. If I do this matrix multiplication, what I'm doing is actually accomplishing this linear combination for every, right? So if we look at one row of B, that's going to be bi of x for every x in our grid, and I'm going to multiply that by the corresponding element of weights and sum. That's what that matrix product does. And then if I do that for every element of x, I'll get a vector with one component for every grid point that's equal to the function value. And so I can plot that, and if I do that, let's see if I can get the plot up here. If I do that, it looks like this. All right. I just got a question. Oh, yes, can I show the plot? Yes, in fact, I just did. So this is what the plot looks like. So again, a lot of people had, I think, a fair bit of trouble with this assignment. I think partly through problems with the linear algebra and partly through the unfamiliarity of working with vectors that are actually functions. So please, please ask lots of questions if you don't understand that, and I can go through any of these steps in more detail. And while we're waiting for questions to come in, I can try to keep going in the lecture. So the next set of lecture notes that you guys needed to look at, let's see if I can bring those up. So here's the next set of lecture notes. Okay, here we go. Can I explain what B2 is again? Yes. So let's go here. Oops, we don't need that one anymore. Here it is. All right. So what I would like to do, right? So what I'm trying to do is for all, what I would like is for xj in our grid, evaluate f of xj, which is equal to sum over I of wi times bi of xj, right? And this, if I have a matrix that evaluates bi of xj, and I call that matrix B2, right? So I'm going to call this matrix B2, then this is equivalent to matrix multiplication. We'll call this B2 of, well, this is going to be matrix multiplication B2 times W, where I have apparently accidentally written the subscripts in the opposite of the usual order, right? So this is matrix multiplication along the I subscript of B2. right? And so what I'm trying to do is compute this matrix B2, whose elements are Bi of xj. And the way I can do that here, right, is each one of those evaluations, I take the difference between one of the grid points, one of the centers, square that, e to the minus half of that squared value, right? And so B2 is the matrix whose ji element is Bi of xj. All right. So hopefully that helps. And here is here are our lecture notes that we're going to go through for this time. So we are done with the segment on linear algebra for a while, and we're going to work now on mixing calculus with linear algebra, right? So we want to be able to take derivatives of functions that involve matrices. And so hopefully everybody is comfortable now with the linear algebra, because we're going to start assuming that you can do the linear algebra and working on layering calculus on top of that. So before we do that, we're going to just briefly do a quick review of scalar calculus, in particular scalar derivatives. And then once we're done with that, people should, as always, ask lots of questions. But once we're done with that, we'll move on to combining that with the linear algebra. All right. So we have a scalar function f, which maps a real argument to a real argument. We're going to write f prime for its derivative. If the argument is called x, we can also write df dx or d by dx of f, right? And so the derivative represents the slope of the function. And so this is now a new function where every output value is equal to the slope of the original function. We can iterate the derivative, so we can make f prime prime, f triple prime, and we'll also write d squared of f by dt squared if t is the argument, d cubed f by dt squared. If a function depends on more than one variable, you can write with this curved d, which is called a partial sign, you can write partial by partial x of f or partial by partial y of f. And what that indicates is the derivative with respect to one of the variables while you're holding the other variables constant, right? So this is called partial differentiation. And then the last bit of notation that we'll commonly use, if we're given a function f of x, we will write f of x with a vertical bar sub x hat as a synonym for f evaluated at x hat. And the reason we do this seems like kind of a weird notation for function evaluation, but the reason we do this is that it's kind of useful to be able to take a bunch of derivatives and then evaluate the result at a point. And if we just use the usual f of x notation, we would have to have x be a variable while we're differentiating, and then a constant after we substitute x hat for it. And so what this does is it separates the part of the expression where x is a variable from the part where we're substituting x with a constant. All right, and so there are a lot of identities that are hopefully familiar for working with scalar derivatives. Some of the most common ones are that that differentiation is a linear operator. So for example, AF plus BG, if you take the derivative of that, you get A times the derivative of F plus B times the derivative of G. And here, A and B are scalars, and F and G are functions. There's the chain rule, right? If we want the derivative of a function composition, f of g of x, then we can write df dx equals df dg times dg dx. Now this notation is suggestive. There's a common mnemonic that basically all we're doing here is we're canceling the dg. But since this isn't really division, we're not really canceling, and it's just a mnemonic, but it's a handy mnemonic anyway. We can also write out the chain rule. D by dx of f of g of x is f prime of g of x times g prime of x, right? And these two things mean the same thing. They're just different notation for the same thing. And then the other common one is the product rule. The derivative of a product of f and g is f times g prime plus f prime times g. All right, and there's a lot of common functions. I'm trying to cover here the ones that we're likely to need in this class. So if you take the derivative of a constant at 0, the derivative of a monomial, x to the k is k times x to the k minus 1. The derivative of sine is cosine, of cosine is minus sine. The derivative of e to the x is e to the x. And if you combine that with the chain rule, you get the derivative of e to the a times x is a times e to the ax, where a is a constant. And you can use that, by the way, to get the derivative of an exponential in base b by rewriting b to the x is equal to e to the x times log b before using this identity. And then the derivative of log x is 1 over x. And again, you can rewrite to handle a different base. All right. So hopefully these scalar derivatives are familiar to everyone. And what I'm going to do, just to make sure of that, is I'm going to post a brief in-class exercise. All right, so this is, it's posted now. There's just a few questions where you guys take some scalar derivatives. So I will wait for a little while people go ahead and do that before we go on with the rest of the lecture. And as always, feel free to interrupt and ask questions while we're working on this, and I'll try and answer anything that, that comes up. All right, so it looks like people are, in fact, remembering their scalar derivatives pretty well. That's good. So a lot of people have already gotten full credit on the exercise. As usual, you have until midnight tonight to finish this. So I'm going to keep going on the lecture notes, and as always, feel free to ask questions about the exercise if you have questions. So we're going to be talking now about derivatives of functions that take vectors as arguments or return vectors. So for a vector valued function, we'll write the function as a column vector of its component functions. And then we'll write its derivative as the vector of partial derivatives with respect to this is a typo. This should read, sorry, let's get a, I'll fix that after class. That should read that df dx is equal to the vector df1 dx df2 dx all the way up to dfn dx. So this here should read that. I'll try and fix that after lecture. For a function with multiple arguments, we can collect the arguments into a column vector and write a row vector of partial derivatives. df dx is the partial with respect to the first argument, second, and so forth up to the nth argument. And the reason we do this argument where one is a column, where one of them is a column vector and the other one's a row vector, is so that the chain rule looks the same as it did for scalar to scalar functions. df dx is df dg times dg dx, but now each one of those is a vector, and when we multiply them, we're doing the dot product between two vectors. And so another way to write it is that the total derivative is the sum of products of component-wise partial derivatives. One of the main uses for a derivative is to write a Taylor series. So a Taylor series is a linear function that approximates some arbitrary nonlinear function in the neighborhood of a point. So here's our nonlinear function, y equals f of x. We'll have a point, x hat and y hat, where y hat is f of x hat. And the first order Taylor series looks like this. Y is approximately equal to y hat plus a times x minus x hat. So there's a matrix A, which is called the Jacobian, or first derivative of f at x hat. And we can write it this way. The ij element of the matrix A is the partial of the I component of y with respect to the j component of x, and we're evaluating the whole thing at x hat. And so this is a linear function, right? It's a vector y hat plus a matrix times a vector x minus x hat. And that linear function, the first order Taylor series, approximates a nonlinear function. People are asking for an example of the chain rule. So sure, let's do an example of the chain rule. How about d by dx of e to the x squared, right? So the chain rule, this is equal to f of g of, so d by dx of f of g of x, where f of z is equal to z squared, and g of x is equal to e to the x, right? So here we can compute f prime of z is equal to 2z. This is using the rule for monomials, right? The derivative of x to the k is k times x to the k minus 1. K is 2, so k minus 1 is 1. and then the derivative of g prime of x, is just e to the x again. The derivative of e to the x is e to the x. And so if we do the chain rule, this is f prime of g of x times g prime of x, and that's equal to 2 g of x, which is e to the x, times g prime of x, which is e to the x again, right? And so this is equal to 2 e to the x squared. All right, and people are also asking for an example with vector derivatives, so I can do that as well. Let's get ourselves a new piece of paper. So let's have our function f of z, so again we have f of x equals we'll have f of g of x, where x is equal to the vector x1, x2, right? And g of x is equal to x1 squared plus x2 squared, and f of z is equal to, I don't know, how about z cubed, right? So now we have df by actually this isn't I mean I can still do this, but this isn't a great example because because the argument in the middle, the argument to f of x is, the argument to f of z is just a scalar, but we can still do df dx is equal to df by dz, dz by dx, which is df dz is 3z squared, and then dz by dx is, well, here g prime of x is the vector that has components 2x1 and 2x2. All right, make sure I got that. Yeah. And so when we do this, it's going to be 3z squared times the vector 2x1, 2x2, and z is x1 squared plus x2 squared, 2x1, 2x2. So that's that example. Let me try and do an example where the thing in the middle is a vector. So let's say now f of g of x, where x is a scalar, g of x is the vector cos x sine x, and f of z is equal to z1 squared plus z2 squared, right? So this one's going to be, I think, a better example. So now we can take the derivative of each one. F prime is going to be the vector 2z1 to z2, and g prime will be the vector derivative of cosine is minus sine. Like that, right? And so the derivative of this is then going to be 2z1 to z2 times the vector minus sine x cos x. And that is there, right? And so if we combine that, right, z1 and z2 are cos of x and sine of x, so this is going to be 2 cos x to 2 sine x vector product with minus sine x cos x. All right, and then we could multiply that out if we wanted to. Minus 2 cosine of x sine of x plus 2 sine of x cosine of x, which is 0, which of course I should have realized when I did this example, because in fact the length of the vector g of x is always 1, and so f of z will also always be 1. 1 squared is 1, and so the derivative of a constant is 0. And so, hey, the chain rule works, and I noticed it told me something that I should have noticed when I made up this example to begin with, that the derivative of a constant is 0. All right, we have some more questions. The derivative of a vector of functions, is that just a scalar number? No, the derivative of a vector of functions is going to be another vector, right? So you take the derivative component-wise of your vector of functions. Do we find the max or min of a vector of functions? No. No, we're not combining these functions with max or min or anything like that. We're just component-wise taking the derivative of the vector of functions. How does this relate to slope? Let's see. It relates to slope. Actually, the best way to see how it relates to slope is to go back to the first-order Taylor series. Right? So here's the expression for the first-order Taylor series. If x and y were scalars, then A would be a 1-by-1 matrix, which is to say a scalar, and we would have that y is approximately equal to a constant, an intercept, plus a slope times x minus x hat, right? And so what we're doing is we're generalizing the idea of a slope to multiple dimensions, right? So it gets kind of hard to visualize in more than 2 or 3 dimensions, but in 2 dimensions you can think of a function with a vector input as being a function whose a function with a vector input, right? So we have a plane of vector inputs. The function rises above the plane, so here's the value of the function, and we evaluate the function at a point, let's say here, and we make a linear approximation to that. And that linear approximation is a plane, and it has a slope in the x direction and a slope in the y direction, right? So instead of being a line with just one slope, it's a plane that has a slope in both directions. All right, so I think we've gone through all of the questions that people have asked so far. Please keep asking them, and I will keep going on the lecture notes. All right, so the main thing that we're going to do when we talk about matrix calculus, we're going to introduce there are, there's a bunch of questions in this example here about why z1 is cosine of x. Okay, so we're doing f of g of x, right? So g of x is cosine of x, sine of x. And then f of z, f is a function that takes a two-element vector as an argument, and z1 becomes the first element of that vector, z2 becomes the second element of that vector. So when we do f of g of x, then z becomes the vector cos x, sine x. And so z1 is cos x, and z2 is sine x. Right? That's what it means to compose a function when the argument is a vector. You compute the vector using the first function, and then hand that off as the argument to the second function. All right, so let's go back to differentials. So the main goal of this section of the course is going to be to teach you a notation that lets you work with vector and matrix derivatives. And this notation is very compact, which makes it a little confusing as you're learning it. But once you've learned it, it can make it extremely fast to take the derivative of an expression involving vectors and matrices. And that's important because for doing machine learning later, we often wind up needing to take the derivative of a fairly complicated function that involves vector parameters or matrix parameters. And so being able to rapidly take that derivative is going to let you follow along when we talk about algorithms that require that derivative. So let's get started on the new notation. So we have the, let's scroll up here to the Taylor series, this here, right? So if we write dy as a shorthand for y minus y hat, and dx as a shorthand for x minus x hat, then this equation here is the same as saying that dy is a times dx. Right? And A is the same matrix as before. It's this one right here, where every component is the partial of one component of y with respect to another component of x. Now, we haven't changed the meaning at all when we write this new thing. All that we've done is define a new notation. And this new notation means still a first-order Taylor series. It describes a linear function of the increment dx, otherwise known as x minus x hat, that tells us the increment in y, right? So a function of the increment in x is the increment in y, and that function happens to be linear. Now, this notation is kind of suggestive, right? If we divide through by dx, which again we're not allowed to do because dy dx isn't really division, but if we divide through by dx, we get dy over dx equals a, which is to say that the first derivative of y with respect to x is a, and that is in fact true, right? A is this Jacobian matrix, which is also known as the first derivative. And so the only difference between the old notation and the new notation is that we've separated dx from dy and given each one its own meaning so that we can move them around separately and work with each one on its own. The other difference is that we've replaced approximately equals by equals. And And that's really only a convention, right? If you think of this as a Taylor series, then these two sides are only approximately equal. What we're going to do is interpret dy and dx in a way that makes this equality be actually true. They're going to be functions of x such that functions of x or y such that this represents the first order Taylor series. But you can think of it as just by convention, we replace the approximately equals by equals because we're thinking of sort of small values of dx and dy where the equality actually holds. All right. So we would like, so just to expand out this notation in a little bit more detail. This matrix is itself, it's a matrix of derivatives, and their derivatives evaluated at x hat. So we can, if we want to be more precise, write that the increment in y is approximately equal to the Jacobian evaluated at x hat times the increment in x. And when we write that as a matrix differential expression, we write dy equals a of x dx. And that is semantically equivalent to this. The only thing is that we've saved ourselves a small amount of ink by suppressing the hat over the x. And again, you can think of that as just a matter of convention. That we don't like having ugly hats lying around, and so we'll suppress them. And it's not going to cause confusion because before, when it was just all of the uses of x hat are now hidden inside dy and dx, and so this x can't be confused with any of those. Okay, we have a question. When we calculate the A matrix in the Taylor series, is that the same plane that the professor just spoke about? Yes, that A represents that, that plane that I was just talking about. So in particular, in the example of a function that maps a length 2 vector to a real number, which is what I was talking about in that example, our matrix A is going to be a 1 by 2 matrix. And the elements of A are going to be the slope in the x direction and the slope in the y direction. It gets more complicated when we talk about a function from R5 to R7, but it's still the same thing. Each element of A talks about the slope of the dependence of one component of y on one component of x when you hold all of the other components fixed, right? So you can think of it either as some high-dimensional analog of a line where you have a slope that's a matrix, or you can think of it as a whole bunch of scalar functions, and the matrix A contains the slopes of all of those scalar functions collected together for easy manipulation. All right. So one of the benefits of our new notation is that it makes it fairly easy for us to distinguish total from partial derivatives. And in fact, we can be even a little bit more flexible than the plain distinction between total and partial derivatives. So if we write an expression like this one, dl equals some function times dx plus another function times dy, what we're saying is that all of the variables that appear inside a differential, here dx and dy, these are the variables that we're thinking about changing. All of the variables that don't appear in a differential, so in this case w, right, those are the variables that we're holding constant. And so here we're saying that the change in L is a function of the change in x and the change in y. And that function depends on the current values of x and y and also w, right? And w we're thinking of as holding constant, and x and y we're thinking of as varying. right? And so again, as a mnemonic, we can divide through by dt, where x and y are a function of some other variable t, and we get that dl dt is f times dx dt plus g times dy dt. And that means, well, that's the correct expression for the derivative of L with respect to t if x and y are allowed to change and w is being held fixed. All right, so we can have an example of a function in our new notation. So here, we're taking a vector x, we're taking a matrix A and a vector B. X is going to be a variable vector, B is a constant vector. We're taking ax minus b, and we're taking the norm squared of that and dividing it by 2, right? So that's our function. And so if we write it out, replacing all of the matrix multiplications and squared norms by just summations and products, you can verify that y is the sum over I of, here's ax minus b, right? Sum over j of aij xj minus bi. And here is that again, so that we have it squared, divided by 2. And so we can take the partial derivative of y with respect to the L component of x. And this here is just using the expressions that I've described above for scalar derivatives. It would be a good idea if you're feeling rusty on scalar derivatives to go through and verify for yourself that this expression works. But when you collect together the terms, you get this expression, sum over I of AIL times sum over j, aij, xj minus bi. And you can recognize these summations as being a matrix multiplication, 2 of them in fact, right? So here we're multiplying A by the vector x, and then here we're multiplying the resulting vector again by the transpose of the matrix A. And so we can write ax minus b transpose times A for this expression here, right? So dy dx is this, because the partial derivatives are as computed there. And so this last line, we can reorganize it into our new notation to be this. dy is ax minus b transpose times a times dx. And this, even though it's a fairly simple expression, it took us several lines of annoying summations to get to the conclusion. And we'll see, probably not this class, but maybe next class, we'll see that we can get this expression directly and quite quickly, much shorter than this small mess up here. We can get this expression directly by working with matrix differentials. And of course, this expression is pretty simple, and so as we start to go to more and more complicated expressions, this sort of derivation where we do it component-wise would get more and more painful, and so we'll be more and more glad to be able to work directly with the differentials. So I think perhaps what I will do is write out that derivation of this expression, write it out in the new notation. And since you haven't yet seen any rules for working with the new notation, you should not expect to be able to produce this on your own yet. But you'll see that there are analogs of the chain rule and the product rule in the new notation. So we have that y is equal to ax minus b transpose ax minus b. And we can just expand that out, right? This is b transpose b minus b transpose ax minus x transpose a transpose b plus x transpose a transpose ax, right? And I haven't done anything surprising yet. I've just written this expression, which is equivalent to this one, and multiplied it out so that I have everything in a sum of terms. And so now we can write dy is equal to, well, the derivative of a constant is a constant, so we can skip that term. Derivative is going to wind up just going through the b transpose a, and we'll get dx. Similarly, it'll be dx transpose a transpose b. And now here, what we'll do is we'll do the product rule, right? So we'll get x transpose a transpose a dx plus dx transpose a transpose a x. All right, and now we're basically done, right? So what we've done is we've used some rules that I will tell you about next time to push the derivative over x inwards. And at this point, we can just collect terms, right? So these terms are all scalars. Dx is a vector, b is a vector, so vector transpose matrix vector, that's a scalar. Same with this, same with that, same with that. And so this and this are transposes of each other, and this and that are transposes of each other. But a scalar is its own transpose, and so we can actually collect them. And so this is equal to minus 2b transpose a dx plus 2x transpose a transpose a dx, right? And this, if we pull out the dx, sorry, if we pull out the a times dx from both terms, it's pretty easy to see that that's equivalent to this one. So again, you shouldn't yet be able to do that derivation yourself, but you can see that each one of these expressions is shorter than the corresponding expression here, and there are no fiddly little sums with all sorts of different subscripts to keep track of, right? Every expression here has only a few terms, and so we can, it's much easier to work with it without making mistakes, with practice. So rather than go into the new set of lecture notes, I think we can end here. I'll start my office hours just a little bit early, and you guys can feel free to continue asking me questions in office hours and on Piazza. All right, thanks a lot. See you guys next time.